Hi everyone, my name is Bob and I will be sharing about my FYP titled Reputation Management System for Blockchain-Based E-commerce. E-commerce accounts for more than a fifth of worldwide retail sales, and 86% of e-commerce buyers have said reviews of the product or service affect their purchasing decision. A related statistic also says that fake reviews cost consumers 12 cents in welfare losses per dollar spent. This brings us to the problems that inspired the project. First is the problem of fake reviews and collusion attacks that plague e-commerce platforms. Sellers create or purchase accounts to leave fake reviews on their own products to boost ratings, or on competitors' products to damage their reputation. It is common to have collusion attacks employing a network of humans or bot accounts and leaving fake reviews in high volumes and frequency. Another problem is that there is no incentive to leave reviews. Typically, buyers who make the effort to leave reviews are the ones who had strong opinions about the product, be it positive or negative. Honest ratings in the middle of the spectrum are often left unsubmitted since there is no incentive to do so. The goals of this project is threefold. First, to create a reputation score system that rewards and punishes users depending on their actions on the platform, by assigning each user a reputation score. Next, a blockchain e-commerce platform is to be developed to allow interactions between buyers and sellers who are governed by the reputation management system. Lastly, a front-end to visualize transactions between users is needed to show step-by-step blockchain transaction data and make sense of the actions performed on the platform. Moving on to the proposed reputation score system. The purpose of the reputation score is to measure a buyer's authority and trustworthiness on the platform. The reputation score of a buyer will directly impact the weight given to this buyer's rating when computing overall average product rating, as per the first formula you see. The reputation score of the buyer also directly impacts the amount of monetary rewards paid out to the buyer for leaving a review, according to the second formula. The amount of monetary reward paid to the buyer is the price of the product multiplied by a percentage set by the seller and the reputation score of the buyer. So how exactly does the proposed reputation score system judge how trustworthy a user is based on his behavior? There are three main factors that the proposed system takes into account, namely the frequency factor, the deviation factor, and the active factor. The frequency factor measures how often a buyer is leaving reviews on a product. This value is between 0 to 1, as is the other two factors. Note that the graphs will show values normalized between 0 to 100 since Solidity does not support floating points. The rationale is that a buyer who leaves a review on a specific product repeatedly within a small time frame is showing abnormal behavior and should be suspected of performing a high-frequency fake review attack. Lambda is the forget constant in the formula, which is used to tune the formula to ensure it correctly identifies high-frequency attacks, while not punishing normal and benign user behavior. Without going into too much detail, the general rule is that the more frequent a buyer reviews the same product, the lower the reputation score should be. Next is the deviation factor. This factor measures how much the incoming buyer's rating deviates from the average product rating. When a product has consistently garnered very positive ratings of say 90 out of 100 across all user reviews, and an incoming rating rated as 0 out of 100, it should be treated with suspicion that it is an attack to unfairly bring down a product's rating. The reverse is true for a product that all users agree is poor, but an incoming rating rates it extremely highly, probably aimed at boosting product ratings. As such, the rationale for the deviation factor is to raise suspicions about transactions following this pattern and dampen its unfair effects through lowering reputation score of the actor. Mu is a tolerance constant used for tuning this component of the proposed formula. Generally, the greater the deviation a buyer's rating is from the average product rating, the lower the reputation score should be. Lastly, the active factor. This factor measures how active the user is on the platform. It follows reason to say that the more a user has used the platform and contributed to it with reviews, the more trustworthy this user is. It is also less likely that this user will be malicious. The general rule is that the greater the number of reviews left by a buyer on the platform, the higher the reputation score should be. After each reviewing transaction, a reputation score, RSI, is calculated for the buyer using these three factors. The updated reputation score of the buyer will be a weighted average of all the previous reputation scores calculated for this buyer. Next, we move on to the implementation of the smart contract e-commerce platform. It is built in Solidity and primarily deployed on the Girly Eve testnet and uses Girly Eve tokens. It allows buyers and sellers to create unique accounts tied to their blockchain wallet addresses and interact with the smart contract. The reputation management system is enforced on this platform. This is the user flow diagram showing how a typical seller and buyer will interact with each other on the e-commerce platform. It will be clearer to explain with a live demo. So the smart contract is deployed on Remix IDE, and we can select the environment to be your own MetaMask wallet. In this case, the MetaMask wallet I already have some test girly ETH, but for today's demonstration purposes, we will go with a local environment called Remix VM. As you can see, there are multiple accounts created, preloaded with test ether for us to test our smart contract. So once we hit deploy, the smart contract will be deployed here. We can see all its functions, as well as we can see that the ether has gone down because it takes some gas to deploy the smart contract. First, let's create a seller. Let's give it arbitrary values for the parameters. And then once the seller is created as confirmed here on the blockchain, we can upload a product. As you can see here, now the product is uploaded. We can check here to see that the count of seller is now 1, and now count of product is 1. We can also check the products of seller by doing this, and checking that indeed the iPhone 15 has been uploaded with a price of 1 ether. This is in units of weight. The next thing to do will be to create a buyer account. So now we have to switch to another address. We create a buyer, and they usually start out with a reputation score of 1. And once the buyer is created, what we can do is to use the buyer account to purchase a product from a seller. So now we have to go and copy the seller's address to input here. Here, the transaction is denied because ethers cannot be 0. Well, this means that to purchase a product, you can't have 0 ether, obviously. And this is a safety check. So now we have amount loaded into our transaction. We can transact successfully. Let's check the purchase products of buyer, and we can check this by using the address. We see that now this particular buyer owns an iPhone 15. So after the purchase product function, the buyer account now has 1 less ether because that was the price of the iPhone 15. This was transferred to the seller account, which has 1 more ether, as you can see here. This is all enforced by the smart contract. In the interest of time, I will now briefly go through the rest of the important functions. So after a purchase, a buyer can now leave a review and give a rating. This buy review function performs an internal call to the calculate reputation score function, which calculates and updates a new reputation score for the buyer. The system then triggers the reward function, which is from the seller side. This reward function, based on this new updated reputation score of the buyer, will calculate the reward amount to pay out to him. This transaction will go from the seller towards the buyer. Let's move on to the simulations and experiments. Amongst the many simulations performed, 7 have been identified to demonstrate the effectiveness of the proposed reputation system and evaluate the performance. Simulation 1 simulates a new buyer account leaving legitimate reviews for 60 transactions on a single product. This is similar to a benign real-world user who practically never purchases and reviews the same product multiple times within a short time window. The reputation system rewards this normal user behavior, and reputation score rises to a full score within 26 transactions, which in this case translates to roughly 1.5 months, a reasonable time to obtain full trust on the platform. Product rating increased slowly initially since reputation of the new buyer was low due to a low active factor. It then increased at a faster rate and became almost linear. Reward amount is based on reputation score, so it follows the exact same trend. Now, let's look at some malicious behaviors and how the reputation score system prevents them. Here, we simulate spam attacks with a new account to boost ratings. New accounts start with a reputation score of 1. The system quickly identifies a high-frequency spam attack, and the user reputation score goes from 1 to 0. Effect on product rating is none, since a 0 reputation score will give 0 weight to this user's rating opinions. Now, instead of using a new account, this simulates a fully trusted account performing the same attack, now starting with a reputation score of 100. Even in this case, reputation score of the malicious buyer quickly plummets to 0, where it stays for the rest of the attack. Even though there's a sharp increase in product rating at the start, the absolute increase of the product rating is almost negligible. Previous attacks were all based on unsophisticated high-frequency attacks. Trying a randomized time gap approach will still see the proposed system perform well. Reputation score is limited between 0 and 4, and the effect on product rating increases at a decreasing rate, overall only increasing the rating by 2 to 3 points after 1,000 reviews. The reward amount also follows the effect on reputation score. Suppose the attacker decides against high-frequency attacks altogether and chooses to automate unfair reviews with long time gaps to avoid detection. In this case, the attacker is able to pretend to be a benign user and attain full reputation score. Assuming the product is only reviewed by the attack has increased product rating to 87. However, this attack consisting of 1,000 long time gap reviews requires 4.33 years to perform. Realistically, there will be many more benign users that are reviewing this product at the same time, and the product rating will gravitate towards the consensus instead. This attack will likely be too long for any attacker to pursue, and not worthwhile for its effects. You might ask, what if the attacker engages in a collusion attack, where he buys multiple new accounts to leave one review each? Leaving one review each will mean that the reputation score penalization does not matter to this attacker, since the accounts are only one use. However, new accounts start with a reputation score of 1, and as seen in this graph, the actual effect on product rating is just an increase of 2.7 out of 100. The estimated cost will be more than $7,000, which is likely a trade-off not worth taking. Employing an army of trusted accounts instead, the attack could achieve good results on product rating, raising it from 10 to 91. However, again the cost will be the limiting factor, as the estimated cost for this simulated attack is over $90,000. In conclusion, the proposed reputation system defends against various types of malicious attacks by decreasing the weightage of opinions of malicious users or making it too costly in terms of both time and money to attack. The system also manages to model normal user behavior on a typical e-commerce platform. The incentive that the system creates will encourage users to leave honest reviews on the platform, which was mentioned to be crucial in affecting buyer decisions and welfare. As for future works, the focus will be on increasing security capabilities against sophisticated attacks, and also tuning the system based on real-world testing. Thank you for listening to my FYP presentation.